Well, looks like we can get started. Welcome back, everyone. Seems like a kind of a small class today, but we'll do the best we can with what we've got. For what we got going on today, we're going to be working on section 11.3, dealing with the integral test. The good news about the integral test is that there's a lot of carryover in section 7.8 with improper integrals, since that's essentially the gist of that test. Analyze the right improper integral to determine if the series was going to converge or diverge. So that's what we're going to be working on today. And as far as the due date, these due dates are in flux. I'm not sure if we'll finish it exactly today. If we need to push the due date and carry this on towards our work on Monday, we'll make that happen. And as far as what's going to happen over the weekend as well, I guess that's Friday and then the weekend, I'm going to start by just getting caught up on all the grading. I always do grading before grading the second exam because when I grade your second exam, I like to give on your exam what your standing is and the course overall. So I'll get caught up on grading, then move over to grading the second exam. But again, there's another contention with this class. The tricky thing is I also have to wait for the exams to come from the various testing centers. I do have the ones for the far out testing centers, but the one in the Pocatello testing center, that one sometimes gets a little bit bogged down. So it could take a little bit of additional time. If they get me the exams on Friday sometime, then I should get them graded this weekend. But if they send them to me on Monday again, then I'll try to get them all graded on a Tuesday. So that's where we're at so far, folks. But any questions at the moment? Okay, well, let's get started then. For the integral test, before we just state the test, let's do just a fast refresher. We're using improper integrals, so the idea is we're actually analyzing this kind of integral. The lower limit is just going to be where the index starts. Sometimes they start at 0, sometimes they start at 1 or 5, so we just match that up. The upper limit of integration will be infinity because our sequences are indexed from 1, 2, 3, and so on off to infinity. So that always matches up. Then the idea is we convert this whole thing into this kind of limit. Say, for example, if it's a particular example, limit as or the integral from 0 to infinity of 1 over 1 plus x squared, we write a limit as t goes to infinity to go from 0 to t. That way, the fundamental theorem of calculus part 2 will work on this. Because t is a finite number, it's still a finite number over here, but then it's affected by the limit, and that's where we pull a value out from right here. So that's just a fast rundown on dealing with these kinds of improper integrals. We're not going to see the second kind at all. It's only going to be this type. Any questions, folks, about dealing with those improper integrals? Okay, so back then and onto our notes. Here's where that kind of stuff comes together. This is the good old integral test. People like the integral test because it's powerful and it's very widely applicable, but it does have some constraints. It has a lot of hypotheses you have to satisfy. The domain isn't always 1 to infinity. It's just going to depend on where your index starts. If your index starts at 5, this goes from 5 to infinity, for example. So the next thing we do is we take our sequence right here, and from that sequence, we define a new function. Essentially, all we do is whatever an is, we write it as f of n. Now we consider it a variable x altogether and integrate on that domain from 1 to infinity. So if that integral converges, we say that the sequence must converge. And if the improper integral diverges, then the sequence has to diverge. So that's the whole statement of the test. It actually takes a lot of words to state all this. But if you're like me, just reading it is never enough. You need some kind of other picture to get some more intuition on what's going on. So that's what we're going to do on all this white space right here. Look at both the cases and see what the integral test is really trying to say with some graphics. Any questions first, folks, with the statement of the test itself? Okay, going down by cases, let's start right here in case 1. In case 1, we have a convergent integral. So let's start just plotting down a generic function that matches this situation. Notice we're only putting down quadrant 1, and that's because our function has to be continuous. It has to be a positive function, so we're in quadrant 1 when we go to write this. And it has to be a decreasing function at the same time. Well, decreasing is important, or else this would be divergent, for example. So if we plug in values 1, 2, 3, 4, just for a couple values, our function might continue on towards the left, have a larger domain, but we only consider it on this kind of domain, right where the sequence starts. So here's the function starting right here. Because we're doing a convergent case, we want to make this one get damped down towards the x-axis rapidly. So that's going to be our generic graph right there. Y equals f of x. So the way this function is defined is in such the way that an, if we put in a number, an integer n, 1, 2, 3, and so on, has to be equal to f of n. So it's going to match here for the value of the sequence. At 2, that's the value of the sequence. And then at 3, 4, and so on. Any questions at the moment with the graph? Okay, so now we say this thing converges. Let's start writing down what a graph might look like. So right at 1, let me use a different color to put this in. Let's go with maybe light blue. If we put in a rectangle that goes up and around like this, then that rectangle represents A1. The reason is this whole area represents A1 because the width is a 1 unit and the height is just the value of the sequence at 1. So this entire area represents the first term of the sequence. We go to this rectangle. This entire area represents A2, the second term of the sequence. This is A3, and so on. They get hard to plot. So let's just use an arrow strategy. A4. So looking at all this, that's kind of nice in a way. We can think of the sequences as being areas. And now, because this converges, here's our next statement. Since the definite integral from 1 to infinity of f of x converges, we have this interesting inequality. Now, it's kind of strange, but we're going to start it at A2 just to get the right statement out. So summation as n goes from 2 to infinity of an. So that's involving this value, the one that's really skinny for A4. I'm starting that summation at 2 because the curve itself starts right at 1, and we developed our rectangles so that they're always under the curve in this kind of way. But this entire summation is going to be less than the limit as t goes to infinity, as we integrate from 1 to t, of the function f of x dx. Well, I wrote less than, but I think the most safest statement could be less than or equals, for example. The reason that's true is if we look at the curve in black, that's the definite integral as t goes to infinity, well, the improper one. All that area is less than the area in the light blue, starting at A2, A3, and A4. You know what? I'm kind of going backwards and forwards on this. I think that is the better statement. It would have been strictly less than. But this is a convergent integral, so this equals some finite number. That's what we mean in the first place when we said the definite integral converges. So we have a finite number right here. We know that that number is larger than the sequence when we start at 2. And the convergence or divergence of a sequence never involves finitely many terms. So sure, we threw away A1, but if the rest of the terms converge because they're less than some finite number, then we get to say here, therefore, n equals 1 to infinity, summation an must converge. And this is by the integral test. The value that this converges to is not equal to the value of the definite integral, sadly, because there is lots of missing area here. But it's just a way to give an estimate. If we have that, this is a convergent sequence, we can come up with a function so that some of the terms are always constrained under in this kind of pictorial graphic. So convergence of the function insists convergence of the sequence. So that's what case 1 is trying to say. If your improper integral is convergent, so too is your series here. Any questions, folks, with that first case? Okay, so that's when it's convergent, and divergent, we should do it as well, just to finish off the notes here. So let's take a look at that case number 2. Just checking if I have enough space. I think we can make that. So for case 2, same kind of graphic, except I don't want my curve to go down towards the x-axis as fast. I want to visually show that it's plausible it diverges instead. So for case 2, let's let our curve go about like this. So we're starting at 1, and the curve is still positive and decreasing. That condition still has to be met, even if it's an improper integral that diverges. So here's y equals f of x. Let's say since 1 to infinity, f of x in case 2 diverges, we have a similar kind of estimate. And to see it, let's plot what the sequence could be visualized as. So same kind of situation, the function matches the values of the sequence. So when we plug in 1 in the sequence, we get this value up here. Plug in 2, and it's this value, and so on down the line. But this time, I don't have to do this little trick to make all the rectangles be under the curve. We can just go this way. So the value of the first term of the sequence is represented by this rectangle this time, A1. And we're using all of that area to represent A1 now. Again, that's kind of cool in a way that because all these rectangles have length 1 and height A1, the area is A1 for every single one of these. At A2, the graph goes like this. Here's for A3. And so on. This one would be A4. But now if we look at this sum, we have something that diverges. And if we add up finitely many terms of the sequence, we're going to exceed the integral itself. So we get to say here, since that integral here diverges, we have that the integral, as 1 goes to infinity, of f of x dx, which is the limit, as t goes to infinity, as we integrate from 1 to t, of f of x dx. This time the integral is smaller in area than all the terms of the sequence. So we would say is less than the summation as n goes from 1 to infinity of an. But if we have a less than going this way, and that integral there diverges towards infinity, this thing being even larger diverges towards infinity just even faster now. So now we get to say, therefore, summation as n goes from 1 to infinity of an must also diverge. So that's the logic of the integral test. The sad fact about the integral test is that it's widely applicable. It's a powerful test, but it takes a lot of steps to actually execute this test. Some of our tests for series are extremely rapid. Think a p-series test or the test for divergence, and even the geometric series test. But this one is not. This one has a good amount of steps that we have to navigate through. But any questions, folks, thinking about the integral test pictorially this way? Okay, so the short of it is, if the sequence is, if the improper integral is convergent, then the sequence itself has to converge. And likewise, if it's divergent, then the sequence itself has to also diverge. So taking that all into account, let's give this all a try. So our first problem of the day is a really random sequence here, n divided by n squared minus 4 to the power 3 halves. We will always want to imagine, could something a little easier work on this? Say test for divergence. But unfortunately, with that particular sequence, if we took the limit as n goes off to infinity of n divided by n squared minus 4 to power 3 halves, this limit comes out as a 0 altogether. Reason for that is the denominator is not a polynomial, but if that -4 was gone, as n gets really, really large, you're really just looking at n squared to the power of 3/2. That's an n cubed altogether with just degree 1 in the numerator. So the denominator, although we can't say it's of higher degree, it acts like a polynomial when n is very, very large, and it would be of higher degree. But the limit is 0, then this tells us test for divergence fails, in the sense that it gives us no information about the convergence or divergence of that series at all. I don't often abbreviate diverges as div just for a shorthand. So if that fails, it's not a p-series, because a p-series has got to look like this. Let's pull up those notes just so we can see what we're referring to. A p-series has got to look like that. Summation of 1 over n to some power. You can't have all of this stuff and still call it a p-series. That's just way more complicated. Test for divergence fails. Not a geometric series at all. N would have to be an exponent, not a base. It's not an alternating series, but we haven't even gotten there. That's not something we really do a lot. So what's left? Integral test. Notice it's way down on the bottom. Reason it's way down on the bottom of this flowchart is because this is one of those tests that are kind of a test of last resort. If everything else fails, you still have at least that one test to go through. We're only interested in the convergence or divergence of that improper integral. And if we have convergence, it matches up with the sequence. And if it diverges, it matches up with the series, not the sequence. And if the improper integral diverges, so does the series as well. So let's give this a try. Any questions, folks, before we launch into integral test on this one? Okay, well, first thing we need is a function, f, and that function f has to match the terms of the sequence. But in practice, all that means is we go over here, analyze the nth term of the sequence, and say, let f of x be equal to x divided by x squared minus 4, the power of 3/2. So now we have a function going. It matches all the terms right here. But there's other things we have to check. A function has to be continuous. Already that's a problem, because if you plug 2 in here, it's not continuous at 2. That's a division by 0. And so that's probably the reason why this one's starting at, say, a 5. 5's kind of random, but that's where we start. So we do have continuity if we were going from 5 to infinity. So let's say this function is continuous. It has to be a positive function. So let's take a look again. That function could be negative if you plugged in, say, like a -2 or something like that. But on the domain from 5 to infinity, it's also a positive function. So we've matched that condition. So this function is continuous, positive. And this is also a decreasing function. We have degree 1 in the numerator. For very large x's, this is just x squared to the power of 3/2 essentially, which is of degree 3. So this becomes a decreasing function on the domain from 5 up to infinity. So if we meet all of those hypotheses, sure, this says domain 1 to infinity, but convergence divergence is never affected by finely named terms. So that could just as well as be a 5 to infinity. They just had to write that theorem once. So we come back over here and begin the improper integral. So we're essentially at this stage, looking at those things, a definite integral from 1 to infinity of f of x dx becomes the limit as t goes to infinity, as we integrate from, there's a mistake there. It's not going to go from 1 to infinity. If our sequence starts at, if our series starts at 5, down below here, our series should start at 5, or our definite integral should start at 5 here as well. So we're going from 5 to t. Then let's just plug in the function. It's x divided by x squared minus 4 power 3 halves dx. So it's kind of cool in a way when a really abstract chapter like chapter 11 intersects so abruptly with what we did in chapter 7, the start of the class, kind of review in its own right? And now solving this problem right here, looks like a U substitution would do the job since there's degree 2 inside that group and degree 1 in the numerator. So we can say let, excuse me, U be equal to x squared minus 4. Its differential, du is 2x dx. So we have a 1/2 du replacing x dx in this integral. So that takes care of the x dx we see here across the numerator. Denominator is just u to the power 3 halves now. And next thing we want to do is get some additional space and change the limits of integration. So upper limit is t, upper limit is x equals 5. When we make the u substitution, upper limit becomes t squared minus 4. And the lower limit becomes 5 squared minus 4 for a value of 21. But let me fix my notation just a bit here. We usually want to convey it this way. U equals t squared minus 4. Makes it a little bit more clear where you're getting that value. Then plug 5 here, and we get lower limit. U is 21. So now we're ready to navigate through this entire thing. It turns into the little bit of space, limit as t goes to infinity. The definite integral now goes from 21 to t squared minus 4. X dx are replaced with, let's see here, a half du. So 1/2 goes in front. I'll throw a du right about here. And u is x squared minus 4. So this becomes 1 over u to the power 3 halves. At that stage, we're about ready to start integrating. So doing this integral, instead of taking a whole nother step, let's just work this out in the margin. We want to find an antiderivative of 1 over u power 3 halves du. So this is just the antiderivative of u to the power negative 3 halves. Antiderivative of that is u to the power add 1. So add 2 over 2 for a positive, or excuse me, still negative 1/2, multiplied by the reciprocal of negative 2. And ordinarily, we'd add a constant, but we don't need to because we are doing this definite integral right here. So scratch work in the margin tells us antiderivative of this is just that right there. So let's go to write out that this is now equal to 1/2. Next, let's put in the value negative 2. Limit t goes to infinity. Antiderivative of this right here is the negative 2 we already put down, and then u power negative 1/2, which is then evaluated from 21 to t squared minus 4. So we're starting to get there. Next thing we need to do is just evaluate the upper and lower limits of integration. So we're now dealing with negative of the limit as t goes off to infinity of, well, when we put in the value here, u to the negative 1/2, well, maybe we'll do that in the next step. Eventually, it's going to go into the denominator with the square root, but no harm in showing that additional step. So let me write it out this way. T squared minus 4, so power negative 1/2, minus 21, power negative 1/2. Because we're still taking a limit as t goes off to infinity, it's a good idea to move this around just to get better intuition on how the limit goes. So now I'm going to drop that to the denominator, make the exponent positive 1/2, which then converts it to the square root. So we have negative limit t goes to infinity of this whole mess. From right here, it's 1 over the square root of t squared minus 4 minus 1 over square root of 21. Now, as t grows without bound, this denominator here gets arbitrarily large, growing ever larger without bound as well. And now 1 divided by something that grows without bound becomes a limit of 0 altogether. So that's gone. That's kind of helpful. And we are just left with -1 multiplying -1 over 21 to get a value of 1 over root 21. We never worry too much about that number. We never even simplify it in this context, because all we cared about in the integral test is whether that is a finite number or not. In other words, we just want to address whether the improper integral converges or not. If you get a finite number, we get to say converges. And here's the original question. This is kind of a long problem. This is not the total answer, though, because all we've said right here is the improper integral converges. So the actual conclusion goes this way. There's my screenshot just for easy reference. We might say, therefore, almost feels appropriate. Triangles just to say therefore, because this is a lot of work. The summation as we go from 5 to infinity of n divided by n squared minus 4 power 3 halves, it must also converge. Must is an extremely strong word in mathematics that's telling us that convergence here is equivalent to the convergence down here for just the sequence. And this is by the integral test. Well, we did it, folks. That's our first one for the day. Kind of a nasty, long, drawn-out problem, but in some sense, it's really just a review problem as well. So thank goodness we covered improper integrals before chapter 11, or else this one could have been a bit of a nightmare, I'd say. Any questions at all, folks? Maneuvering through all those steps? Okay, not every problem is this long. This one got a little bit longer because of the U substitution in the middle. Some problems involve things like that. Could be partial fractions, integration by parts, those kinds of things can come up in this sort of context. Probably not so much on exam because exams are timed. I try to keep the work a little bit more contained. But for the homework, just about everything is on the table. So let's try out another one to get a feel for this even further. Here's one of those kinds of questions for the day. It seems to happen in every section, where we would prefer to have this right here, the series where the nth term of the sequence right here is provided, but that's not what we've got. We just have a listing of numerical values. So let's call these things A1, A2, A3, and so on. So those are the individual terms of the sequence. But we're adding them all up together. That's why we see ... to convey this goes on forever. And so this turns into the summation as n goes from 1 to infinity of an. So with the pluses in the middle, or writing it with sigma summation notation, now it's a series. And really the only way to get through this problem is we need a formula for the nth term of this series, or excuse me, the sequence now, which fills out the series. So let's give this a try. I think this is like the third or fourth one we've practiced, but they're all kind of tricky. They're all a little bit different. What's new about this one is it's not alternating. We only get a 1 in the numerator. And now we need to make some observation in the denominator. Any volunteers for one observation that could be helpful with what's changing?
Adding by 4 every time.
Yeah, good call. If you're adding by 4 every time, one thing you can add down below here is go 4 times n. It may not be exactly what goes there, but when you build these kinds of things, the nth term of the sequence, so you can get the series, we usually are doing trial and error. So even if it's not totally correct, we just make some kind of step and then make fine-tune adjustments as we go from there. So now it's also got to start at a 3 as well. So if it increases by 4, that's a good thought. If it starts at 3, how about just a +3? That doesn't work, but you know what? It's a really good start. Let's see why it doesn't work. If you put in A1, 1 goes there, and we get 1/7. Well, Crap, that's A2. We wanted to get to A1 to go. Looks like there is an adjustment we have to make right on that end. Yeah, go ahead. That does the job. So if n didn't do the thing for us, we just reconvene with a new formula, 4 times n minus 1 plus 3. Let's check it out this way. So if we put in A1 into this formula, well, that's 4 times 0. We just get 1/3. That's encouraging. It matches with our A1 we're expecting. A2, put 2 by the red dot, and we have 4 by 1, so that's 1/7. Plug a 3 in there. It's 4 by 2 for an 8, plus 3 for an 11. At this stage, I'd be totally convinced we've got the right format for the nth term of the sequence. But that's not its most simplified form, so let's do a little bit of extra work on it. This becomes 1/4n minus 4, oh, let me fix that, 4n minus 4 plus 3. So it's 1/4n minus 1. I don't think I would have came up to that originally. That's not how my brain works. I don't think this would be my first inclination. So usually when I try to build this up, my formulas are a little bit more complicated at first as we try to adjust things and make them fit just right. But it's often a good call to simplify them as well because we need to do more with that nth term. But with all that work, we can now say summation as n goes from 1 to infinity of an is equal to the summation as we go from 1 to infinity of 1/4n minus 1. Now, here's where we make the extra determination. Do we have something here that's going to help us out? On the test for divergence, doesn't work. The limit of that thing is 0 because it's constant in the numerator, growing larger and larger in the denominator. So we can't do anything right here. If this was a no, if that limit was not 0, then we would have said it diverges. It's not a p-series because what's wrong? A p-series can't have, oh, didn't mean to scribble on it. A p-series can't have that part at all. So if you're trying to get 1/n to the power p, it's not going to work on this thing. So the minus 1 messes all of that up. It's not a geometric series. Later we'll discover a comparison test is what we really want, but we're just not into that section just yet. All that's left is integral test. So we're going to hit this entire thing with the integral test, which means we need a function. Thinking in terms of that sequence there, we say let f of x be equal to 1/4x minus 1. Now there's 3 hypotheses we have to check. Continuity, we have to check that it's positive and that's decreasing. But looking at this, it wouldn't be continuous if we plugged in a 4th. However, that's not part of the discussion. We're starting at 1 and going forward on this thing. So we can say here, f is continuous. It's a positive function because we're only going from 1 to infinity, so only positive values can occur here. We can't plug in a 0 to get a -1, in other words. So it's positive. And it's certainly decreasing with a constant in the numerator. But to make all of those statements actually correct, we have to give it the domain. We'll say those statements are true on this interval from 1 to infinity. So with this information, this essentially tells us we can now use the integral test. Well, here we are at so far at this step. Integral test on this thing is not so bad. We're going to go from, always watch that lower index. This tells us we're integrating from 1 to infinity, not 5 to infinity like on the last problem, of f of x. It's an improper integral, so we convert it into something that we can actually use the fundamental theorem on. And that's this required step here. Limit as t goes to infinity, as we integrate from now 1 to t, of the function 1/4n minus 1. Oh, let me try again. Not 4n minus 1, it should be n x. 1 over 4x minus 1, we need a continuous function, and now dx. So all we have to do is resolve this one. Actually, that's not too bad. If we have power 1 on our x in the denominator, the antiderivative is the natural logarithm. So we can just immediately say equals, with a little bit of space before limit, as t goes to infinity, the natural log of 4x minus 1. There's a couple additional things that we have to think about and do. For example, I didn't put absolute values on this thing, and that's because of the context. Absolute values aren't important. Because t is going off to infinity, this is always positive. Other thing is, this is not the right antiderivative. There's really a chain rule in here. You differentiate all of this, you get 4 above divided by 4x plus 1. So we counteract with that 4 and just throw in a 1/4 right in front. That avoids the need to have to do a u substitution on this kind of problem. Then we take that whole thing, evaluate it from 1 to t. Actually, we're getting quite far on this one. Sometimes the integral test is a little bit faster. It just totally depends on your integrand. You can imagine if you have to use partial fractions on this, you'd want to look for a way to not use the integral test. But if the integral is pretty fast to calculate, not a big deal to run through the full integral test on this one. So let's plug in our limits. We've got a 4th times the limit as t goes off to infinity of natural log 4t minus 1 minus natural logarithm. We're going to plug in just a 1 on that to get 3. When we go to take this limit, any volunteers to say what would happen to the logarithm function? Is it finite or does it blow up to an infinity? It does, good call. If you're not sure on that one, think in terms of this idea. The graph of the natural logarithm goes like this. It's kind of deceptive because I made my graph look like the logarithm's growing faster than it really would look like on a real axis with 1-to-1 scale. But that is always increasing, just extremely slowly. Because this part goes to infinity, we'll say the whole thing is infinity, and it diverges. But we're referring to the improper integral when we say that. We need to come back in here and say, therefore, our overall conclusion is that the summation, as n goes from 1 to infinity, 1 over 4n minus 1, like the word must here. Must, you don't have to say must, but I feel like it fits. It must also diverge by the integral test. Then that finally finishes off the work on this one. And by the way, like I mentioned, we're going to come up with more and more tests that help us out with this. But one thought you might have had is this has to converge because it looks extremely similar to the harmonic series 1 over n. There was just a linear combination of what's in the denominator, 4n minus 1, that has the same degree. So you could actually think in terms of divergence of this is similar or expected because the harmonic series diverged as well. But to really make that a firm statement, you have to do the comparison test. That's complicated in its own way, so we'll come back to that in later sections. But we've done the integral test 2 ways so far. I have 2 more problems with the integral test on these notes. But first, any questions at all, folks, on getting through these? Okay, that takes us down to this problem. We've been hinting at this since like section 11.1, I think the very first problem. The harmonic series is weird, but it's also extremely important because it's a source of important counterexamples. For example, it tells us that even if the limit of something goes to 0, like over here, test for divergence doesn't do anything for us because The harmonic series satisfies that limit, yet it still diverges. We're going to prove once and for all it really diverges. And the trick to this is we're just going to use the integral test to make that happen. So here's how it goes. For this kind of problem, you do need to know what the harmonic series is in the first place. So if you ever see this, think in these terms. It's a summation as n goes from 1 to infinity of 1 over n. Again, the test for divergence gives us no information. The limit of 1 over n is 0. But we can think in these terms next. Let f of x be equal to 1 over x. Same mantra as before, this is a continuous positive decreasing function. I'll write it officially as then f is continuous. Let's use cont for continuous. Positive, POS is a good shorthand for that. DEC is a good shorthand for decreasing if you just want to say these things with a shorthand. On the domain, 1 to infinity. It's important to say these things out when you're doing your homework as part of the steps. And the reason it is you'd be surprised. You can look at a function and define it this way. When you go to actually write out it's continuous, your subconscious is thinking about it. When you go to say positive, decreasing, your subconscious is thinking about those as well. You might realize that, hang on, I'm not sure if that's actually true now that I've said that. Maybe there's a problem with continuity. There would have been if we started at 0, or maybe it's not actually decreasing. Sometimes decreasing is hard to tell. You might have to use the increasing decreasing test from calculus 1, analyze the derivative and its sign. That's a pretty big problem, I'd say. It's in the reading. But I'd say that's a problem where it wouldn't make it onto exam, too large of a problem, for example. But if all this seems plausible, then we're all set. We're going to go this way. Integrate from 1 to infinity, f of x dx, which means we're taking the limit as t goes to infinity of the definite integral from 1 to t of 1 over x dx. As we do this problem, you might feel like this is deja vu. The harmonic series is, an awful lot similar to this random one, and the work is going to support it. Our work is going to look pretty similar as well. In fact, this is a faster antiderivative. We're just going to say it's equal to limit as t goes off to infinity of the natural log of t. We don't need absolute values since we're going from 1 to t, and t goes to infinity. Then it turns into the limit as t goes to infinity of the natural log of t minus the natural log of 1. That part's 0, but the interesting part is natural log t, like we saw in the last problem, will diverge to infinity as t goes to infinity. So this equals infinity, which tells us it diverges. This is, again, a really super big surprise because when people look at the harmonic series, almost everyone, our intuition tells us it should converge. But this is a borderline case where divergence actually occurs on this one. We'll say for our conclusion, therefore, summation as n goes from 1 to infinity, 1 over n, is divergent. Huge surprise. But any questions, folks, about looking at that harmonic series again? It has the name of harmonic series, but you know what it is really is a p-series. A p-series is anything that involves 1 over n to a power before we put the summation symbol on it. That's 1 over n to the power of 1 altogether. If the power is less than 1, or hang on, I'm on the wrong one. I'm not too sure how to scroll on that. If the power is greater than 1, we say yes, it converges. But if the power is less than or equal to 1, that's the no on this case, we have diverges. This is the case the power is exactly 1, and that's the first case where divergence occurs. The negation of this would be less than or equal to 1. So it's kind of remarkable in a way that somehow the natural logarithm, antiderivative of 1 over x, tied with the harmonic series down here, diverges only because the improper integral for 1 over x also diverges. There's many different proofs of this fact, but I think this is the nicer one. Well, putting this all together, we have a whole new set of tests. They're called the p-series. We were looking at that in the flowchart. Honestly, I didn't invent this flowchart. It's just one that shows up on the internet if you search for convergence divergence flowchart. The thing I don't like too much about it is it shows case where p greater than 1 for convergence. But it's really helpful to just say this as well. Diverges when it's less than or equal to 1. Sometimes spelling it out, it really is important when you're trying to absorb all this new information. So this is that divergent case. When it's exactly 1, that's the harmonic series which diverges. And if your power is larger than 1, by any amount whatsoever, we have a convergent series. So we have an integral test, a p-series test, and I think this one is everyone's favorite. The p-series is probably one of the faster tests to actually use. For example, if it has the format 1 over n to a power, this one's a p-series. Let's start by just writing p-series. I mean, we know it's a p-series, but let's just say it anyway to be specific. Really, the reason I'm writing out converges by integral test or something like along those lines is for our homework questions and our exam questions, these are the two things we're trying to hit. We have to give a conclusion of convergence, divergence, and we have to use the name of the test. If you just say p-series or p-series test at the very start, that does it for me. I know that you know which test we're using. We have to show all the steps of the test, but for a p-series, it's a matter of check if it's in the right format. It is on this one. We have a power p. It's 1.0001, and even though this seems silly, we know it's greater than 1, I'd say it's a good idea to say that right here, because it reminds you we're in this situation. Convergent if p is larger than 1. So we said it's a p-series. We've indicated the test. That's the step. Just tell me what the power is. It's larger than 1, so it converges. That means our work is done. How do you prove the p-series test? Our author uses the integral test on that entire series, splitting it up into cases where p is bigger than 1, less than or equal to 1, and just came up with these conclusions. Well, any questions, folks, with our first p-series? Kind of a nice, refreshing problem you could almost say after doing the long integral tests. Those are drawn out, and this is like the opposite. These are exceedingly fast. But be careful on this one. You might say this one diverges because there's a power less than or equal to 1, but that's not the power p at all. To use a p-series test, you really have to put it in that format. So sometimes these problems turn into exponent work type problems. First thing we've got to do on this one is say it's the summation as we go from 1 to infinity of 1 over n to the power of 5/3. So we just use an exponent law to get the positive power. And now we can say that this is a p-series. Our power p is 5/3. That's definitely greater than 1. So it converges as well. Any questions, folks, with that second one there? Okay, so again, pretty fast. The only trickiness on this was definitely don't say celebrate too early. Once you see something that looks like a p-series, make sure you do all the exponent work to put it in its right format so it's easier to analyze. And here's our next one. This is like the worst case scenario for a p-series. It is a p-series because it's n to a power, divide by n to a power. But what makes it not as friendly is, well, the powers are strange and we need to put the base in one location. So this one is really just an exponent work type problem. We could start off by going this way. It's a summation as we go from 1 to infinity of 1 over n to the power. So we want to keep n in the denominator. That means the power pi minus 1 stays exactly in its position. But then we're subtracting off this power, e minus 1. And that's the format it takes. That's confusing enough because of the symbols that we might as well just write down the formula. A to the power of n divided by a to the power of m is 1 over a to the power of m minus n. So that's what we used right here. It just happened that the n is the entire group e minus 1. Any questions, folks, on that first step there? Okay, simplifying the power on our next step, we get summation as we go from 1 to infinity of 1 over n to the power. Let's take a look at our signs here. We have a -1, but this will turn to a +1 after distribution. So those two are gone. It's really just pi minus e. So we've got a power, or sorry, question first.
The denominator subtracted from the numerator, not the other way around.
So yeah, so the power m would be subtracted from the power n, the numerator, or
That would be n minus n instead.
gotcha. So for a really quick example, imagine it was like, say, a squared over a cubed. You would just get a 1 over a, which tells you, in fact, you're really just taking power 3 minus 2 altogether. So what you would do is you keep the power m in position and you subtract off the numerator power. But I think what causes confusion is we usually see the rule this way. A to the n over a to the power of m is written as a to the power n minus m. That's the typical way to use it. But it all feels backwards because we're trying to match up the p series and keep things down in the denominator. So the subtraction's in a different order.
So I was seeing it the same way as the bottom one, but it's still equivalent. It just would make it a negative, then you just have to move the denominator.
Yeah, exactly. So you're saying if we took this right here, we can put it into the denominator, get a to the power of negative n minus m, and then it would turn into 1 over a to the power m minus n, the same one as above right here. So yeah, that's would all come out as the same thing in the end. Other questions at the moment? Okay, well, we've got a p series for sure. We always knew we did, but the struggle was to find the actual power. So we can say here, p is pi minus e. Would that be bigger than 1 or less than 1? Good call. Pi is about 3 if we round really, really roughly. E is about 2.7. So this is less than 1. It's got to be around 0.3. That's a really rough rounding, but we don't need perfect. We just needed to know it really is less than 1. This tells us immediately this diverges by the p series test. So we did it, folks. Whether you just say it's a p series and do the work over here, or if you do the work and then give the conclusion and indicate that p series test was used, either way, you're doing these 2 bullet points right here. Again, these are the things that we'll be doing for both homework assignments and as well for exams as well. But we did it. That's pretty much how p series goes. Part C is my attempt to try to make it as nasty as possible, but you can't really get that nasty. You're just always going to go to that kind of step. Consolidate your base n to the denominator, analyze the power. So we did it, folks. That's the major content of these notes, but we're not done really. The trouble with sequences and series in particular, is it's kind of like when you're in Calculus 1. You start off with the basic differentiation formulas, but then before you know it, you have the product rule, then the quotient rule, then the chain rule, and then you start to realize every single differentiation formula can now interact in one single problem. Same thing with series. We can give one series where you might start off with something like, say, a comparison test, but then it suddenly requires an alternating series test, something like that. Or we might be doing a Taylor series, and when we're analyzing Taylor series, we analyze convergence divergence on the boundary. One end of the boundary could be a P series, the other end of the boundary could be an alternating series, or maybe one end of the boundary is something complicated and we need a limit comparison test, which then uses some other test all at the same time. So because all of these tests can now interact, the way these sections usually are going to end is like this. We'll list out every test that we put on the table at the moment. It's just these four now. And now we'll do some random problems. Notice it's just part D now. So same instructions as above. Test the convergence divergence, say what test you used, and show all steps. But these are now random. Don't know if it's a geometric series or if it's a P series or something else. So it's up to us to decide what is the right test on every one of them. Starting off with this one, what would y'all say it feels most similar to? Should we use tests for divergence, geometric series, P series? And if all else fails, should we try the integral test? Anyone have a good inclination on that one? I would say its most important feature, just to give a way of a hint, is look where the index n ends up. It's an exponent here and here as well. That gives us a pretty big hint. It's, by that hint, probably one of these two tests. Any volunteers to say which one it definitely has to be? Good call. This one is absolutely geometric, and it's because of that portion right there. We're going to be able to do some work on this, get a common ratio to a power of n minus 1 if we work hard enough. But n is not a base, so that excludes the P-series test. This one's totally out. So that's a great way to think about this one and analyze it. What if we use the test for divergence? That's also out because the limit of 3/5 to a power n is going to be 0 altogether. So we're going to use this test right here, geometric series. That means we should do a little bit of work on that nth term of the sequence right here. So an, we can say that this is 3 times 3 power n minus 1. That takes care of the numerator. We're trying to match up the exact format we see here, starting a summation at 1, the power n minus 1 up here. So let me see if I can just fix this a little bit right here. I think it's a little bit easier to read with everything on the same line. Now for 5n minus 2, write that as 5n minus 1, divide by 5, kind of the opposite of what we did in the numerator, and we have the right powers on both. So splitting this up into the next step, that 5 by the red dot, when we multiply by its reciprocal, ends up here, multiplying 3/5. We have 3n minus 1, 5n minus 1. So altogether, this is 3/5 times 3/5 power n minus 1 when we consolidate both of those bases. So that's the better way to view this thing. Now coming back over here, we can say it's a summation as we go from 1 to infinity of 3/5 power n minus 1. The most important thing about this when we're thinking about convergence divergence is that right there. So we get to say now, R, that's the common ratio, is 3/5. In absolute value, it's less than 1. Usually I just say less than 1 because we're looking at a positive quantity anyways. That tells us, well, if it's less than 1, it converges by the geometric series test. Then that completely finishes it off. The work was put it in the right format so we can analyze it as a geometric series, come up with a common ratio. Less than 1 tells us it converges, and then just say the name of the test. You might have just said geometric series, and that's fine with me as well. Well, again, the hardest thing about part D is that it's not in context. These are series that are mixed up, and we have to start to identify them. But we're going to be doing this work all along as we go through these notes. And I just noticed that that should have said double I. Don't know how that happened. Oh, geez, that's got to be corrected now too. That should have said double I. There's not a third part to the integral test. Let's carry all these down and let's try it out again with one more additional problem. Well, that's a heck of an additional problem, it looks like. You know, if the class is not opposed, just so that we can not run over time, how about we do these out of order? Does that sound all right to folks? Okay, I'll try not to do that too often because that makes the notes look kind of weird. It looks like I don't know the alphabet, something like that's going on, but just so that we're not breaking a problem in half, we're going to have to come back to part E on Monday of next class. So let's make this one our last one. Oh, geez, I want to reveal this stuff below it. This is all new, so let's take a look at every one of these tests that we have so far as we look at this thing. Okay, so going down the lines, it's not a geometric series because n is not an exponent, so that's out. It's not a p-series because p-series has to look exactly like that, 1 over n to a power. We can't do anything algebraically to make that happen. Not a p-series. You know what? The integral test could work. But let's say something bold here. The integral test is a test, again, of last result. Only consider the integral test if you've exhausted all other options. Let's try the test for divergence on this one. So in the test for divergence, we look at an, that's this stuff, and take the limit as n goes to infinity. The limit as n goes to infinity of 5n divided by 7 minus 10 power n. This has an immediate answer, but this is something we're still practicing. Any volunteers to say what this should be? Yeah, exactly. The thought is the degree is 1 in the numerator, degree is 1 in the denominator, so we grab coefficients. 5 over negative 10. Then this becomes the negative 1/2. But what are we looking for? We're looking for that not equals to 0. So even though it seems silly, I encourage you, write this down on your paper. It's not equal to 0 because it preps you for your expectation. Because it's not 0, this is a reminder that the series, as we go from 1 to infinity, 5n over 7 minus 10n, diverges. And this one diverged by, oh geez, let me just rewrite it. Diverges by the test for divergence. So that's kind of a nice one. The test for divergence is one of those tests where we would love to use it as much as possible, but you have to find the case where it does work. And notice the danger in this problem. That's pretty fast. But if we use the integral test on part F, we're probably going to go overtime on this one. Well, maybe not, but it's a ton of writing. We're racing through it. So always do the integral test if there's just no other option. I think that's the bigger takeaway with part F. And by the way, with part E, there is no other option. We need the integral test on that one. And so that's why we're leaving that one for when we come back on Monday's class. So this will be our stopping point for today. Any questions at all, folks, with what we've worked on? Okay, well, pretty soon we're going to have a lot of different kinds of these tests. It's not a bad idea to, even if you're just skimming really rapidly, before you go to read a new section like 11.4, skim through 11.1, 11.2, 11.3, just to refresh yourself on what is on the table so far. Because every new piece of information, it fits like a puzzle a lot more than the other topics in this class have done. So that's what makes chapter 11 kind of challenging, highly, highly interconnected. But we'll come back to these matters next Monday. Have a great weekend, folks. And if you have any other questions, I'll be happy to help out.